Hello my dear students. Today I am going to explain about power from the chapter work, power and energy. So far in the previous classes we discussed about work and energy. Right? Now from this class onwards we will discuss about power. Right. First, what is meant by power? Very simple definition is there. That is the rate of doing work. The rate of doing work is called power. That is how fast or how slow your work is done. Okay, that means the power is a measure of how fast or slow your work is done. Work is done. For example, if a person take very smaller time to do a particular amount of work, then his work is, his power is said to be greater. Okay, if a person take very smaller time to do a particular amount of work, then his power is said to be greater. Okay, suppose if you take more time for doing that work, then his power is said to be lesser. Okay, if we take a smaller time for doing particular amount of work, his power is greater. If we take more time, if we take more time, then his power is lesser. Power is lesser. So the definition of power is rate of doing work. Rate of doing work is called power. Another some definitions also there. The work done per unit time, the work done per unit time, or the rate of consumption of energy, rate of consumption of energy, or the amount of energy transferred or consumed. The rate of, the amount of energy is transferred or consumed per unit time is called power. So these are the definitions of power. Okay, the simple definition is the rate of doing work. Other definitions are work done per unit time, rate of consumption of energy, or the amount of energy delivered or amount of energy transferred per unit time. Per unit time. Unit time means 1 second. Okay, so these are the definitions of power. So power is given by the formula work done divided by time taken. Work done divided by time taken. Power is denoted by the letter P. It is given by the formula P is equal to W divided by T. Okay, power is denoted by P. It is given by W divided by T. That is work done divided by time taken. The rate of doing work is called power. Right. There are two types of power: average power and instantaneous power. First one is average power and the second one is instantaneous. Average power and instantaneous power. So first we go for average power. Okay, what is the average power? Very simple. The average power of a person or average power of an engine is defined as the ratio of total work done to the total time taken. The ratio of total work done to the total amount of time taken is known as average power. So average power is denoted by P suffix avg. It is given by total work done divided by total time taken. Total time taken. So the average power is defined as ratio of the total amount of work done to the total time taken. Total time taken. Right. For example, suppose a person does a work of 100 joule in 2 seconds and 50 joule of work in 1 second or another 2 seconds, and next to 25 joule of work in next to 2 seconds. Again it does 25 joule of work in another 2 seconds. Right. What is the average power of a person for doing these works? Okay, how can you calculate? Very simple, by using this equation. Okay, what is the equation? Average power is equal to total work done divided by total time taken. So first we need to calculate the total work done by the person. Right, what is the total work done by the person? 100 joule plus 50 joule plus 25 joule plus 25 joule. So 100 plus 50, 150, 150 plus 25, 175, 175 plus 25, 200. So total work done by a person is 200 joule. Right. Next, what we want to calculate? Total time. So what is total time taken? 2 seconds plus 2 seconds plus 2 seconds plus 2 seconds. So total time taken by the person for doing what does 200 joule of work is 8 seconds. 8 seconds. So total work done 200 joule, total time 8 seconds. Right. Now substitute these two values here. Then average power of a person is equal to total work done by the person 200 and total time taken is 8. Right, 200 divided by 8 or 100 divided by 4 or 50 divided by 2 or 25. So 25 joule by second. It means on average he does 25 joule of work for each and every second. Okay, average power of a person is 25 joule per second. It means he does 25 joule of work for every second. Okay, so average power is defined as the ratio of total work done to the total time taken, to the total time taken. Right. Next we go for instantaneous power. Instantaneous power. Right. The power at any instant is called instantaneous power. The power at any instant is called instantaneous power, or the power consumed or power delivered at a given interval of time or given instant of time is known as instantaneous power. Instantaneous power. Instantaneous power is denoted by like this, and it is given by dw divided by dt, or otherwise limit this del t tends to becomes 0 into del w divided by del t. So instantaneous power is given by P suffix instantaneous is equal to small dw divided by small dt, or another formula, instantaneous power is equal to the limit of del w divided by del t as del t tends to becomes 0. As a del t tends to becomes 0, that is del t approaches 0. Right. So these are the expressions for instantaneous power, and average power is equal to total work done divided by total time. Right. Once again, I repeat what is meant by average power and instantaneous power. Average power is defined as the ratio of total work done to the total time taken, whereas instantaneous power is defined as the power at any instant is called instantaneous power, or power delivered at a given instant of time is known as instantaneous power. Instantaneous power is given by dw divided by dt, or limit del w divided by del t as a del t tends to becomes 0. So these are the two types of power. Right, already I told the power expression is P is equal to W divided by T. Right. We know that the unit of work done is joule. The SI unit of work done is joule. And SI unit of time is second. SI unit of time is second. So the unit of power, or SI unit of power, is joule per second or Watt. A scientist name watt is a unit of power. So SI unit of power is watt, or the one, I mean watt equivalent to unit is joule per second. Joule per second, right? And some larger units of power also there. Some other units also there. They are kilowatt, megawatt, and horsepower. Okay, so these are some other units of power. The practical unit of power is horsepower. The practical unit of power is horsepower, right? So kilowatt, megawatt, and horsepower, these are other units of power, right? 1 kilowatt is equal to 1000 watt, or 10 power plus 3 watt. And 1 megawatt is equal to right 1 lakh watt, or 10 power plus 6 watt. And 1 horsepower is equal to 746 watt. 1 kilowatt equal to 10 power plus 3 watt, and 1 megawatt is equal to 10 power plus 6 watt, and 1 horsepower is equal to 746 watt. Horsepower is a practical unit of power. Practical unit of power. To express greater amount of power, we can use a horsepower. Okay, for the electronic, the vehicles. For vehicles, lorry, bus, their power is generally represented by the unit called horsepower. 1 horsepower is equal to 746 watt. 746 watt. Next, the dimensional formula for power. Dimension. Dimension of power is, we know that power is equal to work done divided by time. The dimension of work done is m power 1, L power 2, and T power minus 2. Okay, already I discussed in the previous class. The dimensional formula for work done is m power 1, L power 2, and T power minus 2. And dimension of time is T. Right now, take T numerator. Then this term becomes m power 1, L power 2, T power minus 2 into T power minus 1. Or m power 1, L power 2, T power minus 3. So this is dimensional formula for power. Dimensional formula for work, m power 1, L power 2, T power minus 2. Whereas dimensional formula for power is m power 1, L power 2, and T power minus 3. T power minus 3. And power is a scalar quantity, because it has only magnitude. It has only magnitude. So power is a scalar quantity. But it can be written in vector form. The vector form of power is equal to P is equal to F vector dot V vector. Right? This is relation between velocity and power. Later we will discuss about that. So this is vector form of power. P is equal to F vector dot V vector. That is the dot product of force and velocity is nothing but power. This is a vector form of power, but generally work done is given by the formula P is equal to W divided by T. It is a scalar quantity because it has only magnitude, and it's a dimensional formula m power 1, L power 2, and T power minus 3. And SI unit of power is watt, and other units are kilowatt, megawatt, and horsepower. 1 kilowatt is equal to 10 power plus 3 watt, 1 megawatt is equal to 10 power plus 6 watt, 1 horsepower is equal to 746 watt. 746 watt, right? When the work done by a person is said to be 1 watt. When the power delivered or power of a person is said to be 1 watt. Simple. If we do 1 joule of work in 1 second, if a person does 1 joule of work in 1 second, then a power of person is said to be 1 watt. So power is said to be 1 watt, or power of a person is said to be 1 watt. When? If 1 joule of work is done, 1 joule of work is done in 1 second. In 1 second. Okay, then power is said to be 1 watt, or power of a person is said to be 1 watt. So 1 watt is equal to 1 joule per second. 1 watt is equal to 1 joule per second. Suppose if a question is asked like this, define a unit of power, then we can write the power is said to be 1 watt if 1 joule of work is done in 1 second. 1 second, right? What is power means? The rate of doing work is called power. Right. We know that the work done by the force, suppose F vector, for displacing the body through a distance of dr vector is given by W is equal to integration of F vector dot dr vector. Okay, this is work done by the force for displacing the body through a distance of dr is given by W is equal to integration of F vector dot dr vector, right? So this is left hand side of the equation, this is the right hand side of the equation, right? Here W is nothing but total work done, total work done. Okay, total work done is nothing but integration of small work done. Okay, by integrating small work done, we can get to total work done, right? Already you familiar about that. By integrating small work done, we can get to total work done. So here total work done W can be written as integration of dW, integration of dW, right? For our convenience, this term is multiplied by a small time, that is dt. Small time is generally represented by like this, dt. For our convenience, in this term, both numerator and denominator is multiplied by dt. So W is equal to integration of dW, or for our convenience, integration of dW into dt divided by dt. Suppose this is taken as equation number 1 and this is for equation number 2. Equation number 2. So the left hand side of this equation can be written as integration of dW, and integration of dW for our convenience can be written as integration of dW divided by dt into dt. If same value is multiplied in the numerator and the denominator, this value cannot be changed, right? So W is equal to integration of dW divided by dt into dt, right? And next, right hand side of the equation. Right hand side, F vector dot dr vector. F vector dot dr vector. Right? In this term also multiplied by dt in both numerator and denominator. Right? Like this. Integration of F vector dot dr vector divided by dt into dt. Integration of F vector dot dr vector divided by dt into dt, right? Here dr vector is nothing but displacement. dt time. We know that the rate of change of displacement is called velocity. The rate of change of displacement is called velocity. So velocity v vector is equal to dr vector divided by dt. So integration of F vector dot dr vector is equal to integration of F vector. Instead of dr vector divided by dt, we can write v vector into dt, right? Substitute, suppose this is equation number 3. Now substitute equation number 2 and equation number 3 in equation number 1. So instead of W, integration of dW divided by dt into dt. Instead of integration of F vector dot dr vector, we can write integration of F vector dot v vector into dt, right? So equation 1 becomes integration of dW divided by dt into dt, which is equal to right hand side integration of F vector dot dr vector is equal to integration of F vector dot v vector into dt, right? Now take this term on left side, integration of dW divided by dt into dt, okay, minus integration of F vector dot v vector into dt, which is equal to 0, right? Here integration and dt are common, so take outside. Then this equation becomes integration of dw divided by dt minus f vector dot v vector into dt is equal to 0. So dt is common in this two term. So take outside, and integration also common. So this term can also be written as integration of dw divided by dt minus f vector dot v vector into dt is equal to 0, right? And this equation is applicable for all values of time, that is a dt. For any value of time dt, this equation is applicable, that is integration of dw divided by dt minus f vector dot v vector into dt is equal to 0. So this equation is applicable for all values of time dt, right? Okay, and one more thing. So in this term, the value within the bracket, that is dw divided by dt minus f vector dot v vector is equal to 0. Okay, why? Let I explain. So dw divided by dt minus f vector dot v vector is equal to 0. That is, in this equation, the value within the bracket should be 0, right? dw divided by dt minus f vector dot v vector equal to 0, or dw divided by dt is equal to f vector dot v vector. We know that dw divided by dt is nothing but the rate of doing work is called power. So power P is equal to f vector dot v vector. P is equal to f vector dot v vector. Here f vector dot v vector is the power, and dw divided by dt value also power. So if both power values are subtract, then we can get 0. So that is why in this equation, the term within the bracket should be 0. So that is why I am right, dw divided by dt minus f vector dot v vector equal to 0. Therefore dw divided by dt is equal to f vector dot v vector, or dw divided by dt is nothing but power. So power P is equal to f vector dot v vector. So already I told, the dot product of force and velocity is nothing but power. So this is a vector form of power. So far we discussed about power and different types of power and the relation between power and velocity. Right? A simple definition of power is rate of doing work. So this is common definition for all types of power. But especially for electrical power, the definition is just differ. That is, the rate of doing electrical work is called electrical power. Right? And or rate of consumption of electrical energy is called electric power. The rate of consumption of electrical energy is called electric power. Okay, right. That is, how fast an electrical appliance consumes energy, or how slow the electrical appliances consumes energy is per unit time is referred by the term is called electric power. So electric power is defined as rate of consumption of electrical energy or rate of doing electrical work. Right? What is meant by electrical energy? Simple. The capacity of to do electrical work. So to do any work, we need a capacity. So to do any work for electrical appliances, it has some capacity. So the capacity to do electrical work is called electrical energy. Right? Already I told the unit of power is what? The SI unit of power is what? The SI unit of electrical energy is joule. SI unit of electrical energy is joule. But the practical unit of electrical energy is kilowatt hour. SI unit of electrical energy is joule and practical unit of electrical energy is kilowatt hour or watt hour. Watt hour or kilowatt hour, right? Okay, when the electrical energy consumed by the electrical appliances is said to be 1 kilowatt hour. 1 kilowatt hour, right? Okay, 1 kilowatt hour is nothing but the electrical energy consumed by the electrical appliances. Electrical energy consumed by the electrical appliances at the rate of 1 kilowatt in 1 hour. At the rate of 1 kilowatt in 1 hour. It means, suppose let us consider any one of the electrical appliances. If the power consumed by this electrical appliances is suppose 1 kilowatt. The power consumed by this electrical appliance is 1 kilowatt. Okay, in in 1 hour. So within 1 hour, the power consumed by this appliance is 1 kilowatt. 1 kilowatt. Then what is the electrical energy consumed by this appliance? The electrical energy consumed by the appliance becomes 1 kilowatt hour. So the electrical energy consumed by these electrical appliances is 1 kilowatt hour. If it consumes 1 kilowatt of power, 1 kilowatt of power in 1 hour. 1 kilowatt of power in 1 hour. Okay, simple. The electrical energy consumed by the electrical appliances at the rate of 1 kilowatt in 1 hour is known as 1 kilowatt hour. So kilowatt hour is the practical unit of electrical energy. Okay, right. So 1 kilowatt hour equivalent to joule value is 1 kilowatt hour is equal to 3.6 into 10 power plus 6 joule. Okay, this is because 1 kilowatt can be written as 1 kilowatt into 1 hour. 1 kilowatt into 1 hour. Already I told 1 kilowatt is equal to 10 power plus 3 watt. 1 kilo is nothing but 10 power plus 3. 1 hour is equal to 60 into 60 second. 60 into 60 second. Right. So 1000 into 60 into 60, 3600 watt second. Watt second. Right. Or 36 into 1, 2, 3, 4, 5. So 10 power plus 5. Or this can also be written as 3.6 into 10 power plus 6. Watt second. Watt second is nothing but joule. So 1 kilowatt hour equivalent to joule value is 3.6 into 10 power plus 6 joule. Right. So electrical energy means the capacity of to do electrical work. The capacity of to do electrical work is called electrical energy. The electrical energy consumed by the appliances is said to be 1 kilowatt hour if it consumes 1 kilowatt of power in 1 second. 1 kilowatt hour equivalent to joule value is 3.6 into 10 power plus 6 joule. 3.6 into 10 power plus 6 joule. Right. Based on power region, some problems are given our textbook. First example problem 4.18. Question is, calculate the energy consumed in electrical units. Calculate the energy consumed in electrical units when a 75 watt fan is used for 8 hours daily. 8 hours daily for 1 month. The electrical appliance is electric fan. The power rating of a fan is 75 watt. 75 watt. Okay, it daily operates 8 hours. 8 hours. What is the total electrical energy consumed by the fan for 1 month? We need to calculate, right? Before going to this, we know that power is given by the formula P is equal to W divided by T. Power P is equal to work done divided by time. Work done is nothing but electrical energy consumed. Energy. Okay, work done, because both work done and joule has the same unit. So power is nothing but rate of doing work or rate of consumption of energy. So power can also be written as P is equal to work done divided by time or energy divided by time. Energy divided by time, right? Therefore, energy is equal to power into time. Energy is equal to power into time. If power is electrical power means then energy becomes electrical energy. So electrical energy is given by the formula E is equal to power into time. That is electrical power into time taken, right? So now first what we want to do, first we need to list out what are the given values in this question. So what are the given values? Power value is given, that is 75 watts. 75 watt, right? And time T is equal to 8 hours. Time 8 hours, right? And total time is 1 month. 1 month, that is 30 days. 30 days is given here, right? What we want to find out? Energy consumed. That means electrical energy consumed. Energy, right? What is the formula for energy? Energy is equal to power into time taken. Power into time taken, right? So here energy means the energy consumed by the fan per day. The energy, that means electrical energy consumed by the fan per day. First want to calculate. Power of a fan is 75 watts and time taken is 8 hours. 8 hours, right? 5 8s are 40, 8 7s are 56, 56 plus 4, 60. So 60 watt hour, right? And next we want to change watt hour into kilowatt hour, right? So 600 watt hour or 0.6 kilowatt hour. So this is electrical energy consumed by the fan for 1 day. For 1 day. Right. And 1 kilowatt hour is nothing but 1 unit of electrical energy. 1 kilowatt hour is nothing but 1 unit of electrical energy. So energy consumed by the fan per day is equal to 0.6 units. 0.6 units, right? What we want to find out? The energy consumed by the fan for 1 month. 1 month. Therefore, total energy consumed by the fan is equal to energy consumed by the fan per day into total time. Total time. Energy consumed by the fan per day 0.6 units. And total time is 30 days into 30. So 30 into 30 into 0.6, 18. So 18 units. So total electrical energy consumed by the fan for 1 month is 18 units or 18 kilowatt hour. 18 kilowatt hour. So this is very simple problem in power region.